Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 15, 2025, about 3 days ago. The headline result is a single compact recurrent policy that controls a wide range of Quadrotors zero-shot with a tiny 3-layer network of only 2,084 parameters that adapts in flight-through in context learning. The paper is titled RAPTOR, a foundation policy for Quadrotor control, and as we will see later, the real-world demonstrations are striking. In short, the approach distills many specialized teacher controllers into one foundation policy, enabling robust sim-to-real transfer and recovery under disturbances without per-platform retraining. On X, posts highlight a tiny foundation policy that flies many Quadrotors zero-shot, with tests on 10 platforms from 32 grams to 2.4 kilograms and millisecond adaptation. Engagement appears moderate, with likes around 50 to 90. Alright, the previous segment set the headline result. Figure 1 illustrates why this matters and how the method works. Panel A contrasts human quick adaptation with typical reinforcement learning controllers that need system identification and retraining, while the right side proposes rapid zero-shot adaptation. Panel B shows the pipeline. Many teacher policies are trained across a wide dynamics distribution, then a compact recurrent student learns by meta-imitation, which enables in-context learning from observation action history for deployment across different Quadrotors. Okay. Figure 2 reports how training progressed and what design choices matter. Panel A shows that all 1,000 teacher controllers reach long episodes quickly, which signals stable reinforcement learning despite diverse dynamics. Panel B presents the student's meta-imitation learning, where performance on 7 unseen platforms rises steadily and converges by about 1,000 epochs, with heavier models improving more slowly. Panel C traces diminishing returns as the number of teachers grows, so a few hundred, already near the top. Panel D indicates a hidden size around 16 balances accuracy and tiny inference compute. Alright, the previous figure quantified scaling and compute. Figure 3 demonstrates what the policy actually does during flight. The top panels show recovery from a tough start, with position and orientation errors decaying as the drone rights itself. The center heat map tracks the hidden state, which evolves smoothly because the recurrent policy infers dynamics from history. The regression plot then shows linear probing of that latent state, which predicts thrust to weight with high accuracy. The bottom curve confirms the estimate improving over time. Well, the previous figure established that the policy learns useful dynamics in its hidden state. Figure 5 shows how that translates to trajectory tracking across platforms. The panels plot figure 8 paths at 3 speeds, where colored traces match the reference loops closely and encode speed. The bottom table reports root mean square error and maximum velocity, which remain competitive across 10 real drones and 2 simulators. Performance holds even at the fastest interval, so the controller generalizes while staying stable. Wrapping up, 2 takeaways stand out. A tiny recurrent controller with just 2,084 parameters can adapt in flight across wildly different drones, and meta-imitation over many teachers delivers robust sim-to-real transfer without per-platform tuning. The broader implication is practical, foundation-style control on commodity hardware. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.